Hi everyone! In this video we will talk about what a neural network is and how it works, discovering the maths that makes a computer capable of learning. And later we will implement one using Python. But first of all, why is a neural network called like that? An artificial neural network, or simply a neural network, is a computational model inspired by the neural networks in our brains. We as humans have around 86 billion neurons in our brains that receive input from our senses and provide output in the form of stimulus. Through our senses, we can perform various activities, such as playing chess or classifying objects. For example, we can decide on the next move in a chess game based on what we see on the board. But adequately answering a question requires a learning process. In fact, if we are playing chess, our decision is not only based on what we see, but also on our prior knowledge of chess. And we all know that the more we play chess, the better we get. This is exactly what an artificial neural network does. It receives an input and provides an output based on knowledge acquired during a learning phase. In this video, we will take a deep dive into the mathematics behind a neural network and see how a neural network makes decisions and learns. Formally, a neural network is a computational model that makes a computer capable of learning. It is composed of units, also called neurons, of course a highly simplified model of a neuron in the human brain, arranged in layers and connected to each other. The output of one unit is the input of the units of the next layer. The first layer is called the input layer, and the number of units of the input layer depends on what we want to classify. For example, if we want to classify a digit written on a 28 by 28 image, we can transform the image into a vector of 784 elements that corresponds to the grayscale value of each pixel in the image. So for this reason, the input layer will have 784 units. The last layer is called the output layer, and as before, the number of units depends on the problem. If we consider the same example, that of digit recognition, there are 10 possible classes, therefore there are 10 units in the last layer. The layers in between are called hidden layers, and they will always have the same number of units. At this point, we have mentioned the unit too many times, I think, but what is it? We can see it's a black box that takes a real vector of n elements and produces a real number. Inside this box, there is a linear model, which simply means that we are talking about a linear function, where each independent variable x is associated with a parameter w, commonly called weight. And weights are where the knowledge of the units resides. In fact, each weight indicates how important that input is for making a decision. In conclusion, we are just dealing with a weighted sum. But a neuron, or a unit, whatever you want to call it, is not just a weighted sum. It is necessary to feed an activation function with result of the linear model. This function, as the name suggests, indicates for which range of values the unit can be activated. Some might ask, why do we need an activation function? It is very simple. If we only use the linear model, and if we stacked several layers, our neural network would only represent a linear function. In fact, the composition of linear functions is still a linear function. The entire neural network would only represent a simple straight line. And to put it simply, we cannot do much with a straight line. By using a non-linear activation function instead, we can introduce non-linearity in the neural network. And this means that we can represent more complex relationships within the data. There are different activation functions: the sigmoid function, the rectified linear unit, the leaky RLU. Each function has its pros and cons. But for this video, I will use the rectified linear unit, a very simple function that gives 0 for negative values and the value itself if it's positive. There is one small thing I didn't mention before. To the weighted sum is added a bias, a parameter that is not associated with any variable, but it's useful for regulating the behavior of neurons that tend to active more or less easily. It basically shifts the activation function. We can now imagine the neural network as several units that have their own linear model and that are interconnected between them. The outputs of the neurons of one layer are the input of the neurons of the next layer, and the process repeats again and again. Each neuron will have its own weight and will process the output until it's reached the output layer. This process is called forward propagation, and this is the part of the whole algorithm where the neural network makes decisions, bad or good as they are. Now, I would like to give more formalism on how forward propagation works. We can represent a layer with n units as a column vector of n elements, so we have x1, x2 to xn, and we call this column vector x. Then we consider the next layer composed of only one unit, and from this unit we want a number that we denote as a, and then the weights, we have w1 that is associated with x1, w2 with x2, and so on to wn, can be represented as a row vector of n elements. Okay, we have w1 to wn, and we denote this row vector as w. And then the linear combination that I showed you before, z, that is just this sum that I showed you earlier, wi, xi, can be performed with one single operation, that is the matrix product between w and x. Then a is just the activation function fed with the linear combination between the weights and the input. To be honest, it seems very easy to compute this part, to forward input from one layer to the next one. But now, if we consider a next layer composed of m units, so we have here m units, the input coming from the previous layer is still a n element column vector, but now the weights can be arranged into a matrix. So we have here a matrix, and we have w11, w12, w1n, and here we have here we have wm1, wm2 to wmn, mn. Here we have a matrix of dimension m by n, where each row corresponds to the weight associated with the input for the linear model of each unit in the next layer. So, for example, the element w12 can be seen as the weight associated with the second input for the linear model of the first unit in the next layer. So this weight right here. Okay. But when dealing with linear combinations, I think that it's very useful to understand the dimension of the operands. So Z is the linear combination between the weight and the input. The weights are arranged into a matrix m by n, this is the weight matrix, of sides m by n, and x is a column vector of n elements. From this matrix multiplication, we obtain a column vector of m elements, and this is exactly what we want. In fact, from the next layer, we want a column vector that we denote as A of m elements. A is just the activation function fed with our linear combination. And since the activation function works element-wise, our results doesn't change. It's still an m by 1 column vector. And that's the definition of A. For the hidden layers, we will consider the rectified linear unit activation function. Only for the last layer, we will use the softmax activation function. It is very useful to make the output of the forward propagation step more readable. Instead of seeing a meaningless value, for example 130 for the first unit of the last layer, we read 0.96. It means that there is a 96% chance that the input given to the neural network belongs to the first class of our classification problem. This is what this function is usually used for, highlighting the largest values and hiding those that are significantly smaller than the maximum value. Okay, so now we understood how a neural network makes decisions, but what is missing is how it learns. In order to do that, it has to adjust its weight according to the magnitude of the error made. And how much the network must adjust the individual weights is based on the impact of each weight on the wrong decision. During training, the network makes its prediction, then it is compared with the correct answer, and based on that, the weights are adjusted. This is the essence of supervised learning algorithms to which neural networks belong. We train our model with data whose label
is unknown to the neural network, the model makes its prediction, and then the label is revealed. In this way, the neural network can quantify how wrong its prediction was. To make things clearer, imagine that you want to learn how to classify types of flowers. You have a catalog of flowers, and you know what types of flowers there are. Initially, you make random decisions, and maybe some right, but probably most wrong. After each decision, the flower's label is revealed, and several attempts later, to give an example, you begin to successfully recognize a daisy simply because the center of the flower is yellow. So, if the flower has a yellow color in the center, you know for sure that it's a daisy. But then, you begin to erroneously claim that a dial is a daisy. This is due to the fact that your decision was strongly influenced by the color of the center. And we can see this information numerically as a great weight associated with the input center color. We must therefore change the way we rely merely on the color of the center and consider the color of the petal, for example, a little bit more. This is the way neural networks learn. But now we need to understand numerically all these ideas work together to make a group of neurons capable of learning. First of all, the neural network is trained with a training set, and for every training example, we need to quantify the error between the predicted value and the real label. Just consider a one-class neural network with one unit in the last layer that indicates if the training example belongs or not to the class. To quantify the error between the predicted value and the label of a single example, we can use a cost function that is the square difference between the two values. And if we consider the training set, the cost function will be the mean squared error. But for now, to better understand how all these concepts work, let us consider a single training example and a single class classification, so that we can deal with simple real numbers. Later, I will scale all the concepts to vector and matrix operations, so that we can deal with more training examples at a time and more classes. Back to what we want to achieve, we want to minimize the error in order to obtain more accurate predictions. In fact, minimizing the cost function is the core process of the learning phase, and the only way to do this is by adjusting the weights and biases. Okay, so this graph represents the cost function j based on two weights w1 and w2. And I think it's very useful to get a visual perspective of what we want to achieve. In fact, our goal is to reach this lowest point, because here is where the network commits small errors. Initially, the network will choose the initial weight randomly, so we can start also from here, and then the algorithm will take small steps towards this lowest point. Right now, I'm seeing the graph on my screen, so for me, it's very easy to know where I have to go, the direction of each step. But for the algorithm, it's a little bit different, because it has to compute the gradient of the cost function in order to know the direction of each step. In fact, the method we are going to use to find the optimal weights is called gradient descent. But since the network chooses its initial weight randomly, the algorithm can also start from here, and then step by step, it will reach this local minimum. And this point seems to be good, but not as good as this global minimum. And by this, I mean that we have to be a little bit lucky with the initial weights. The size of each step is defined by the learning rate that we are going to call alpha. And this is a parameter that we are going to choose, and we have to be a little bit careful choosing alpha. Because if we choose an alpha that is too large, the steps will be too large, and the algorithm might diverge. If we choose a too small learning rate, the algorithm may require too many steps to reach the lowest point. We have to try different learning rates in order to use the optimal one. Before explaining how gradient descent works, it is useful to know what the gradient of a function is. To explain it simply, let us consider a function that takes as input a vector of n variables. The gradient is a vector of n elements that correspond to the partial derivatives of the function with respect to each variable. For example, the first element of the gradient corresponds to the partial derivative of the function with respect to the first variable. The gradient is a very useful tool because it points in the direction in which the function is at its maximum. And since we want the opposite, we only need to consider the negative gradient of the cost function. In summary, in order to learn, the neural network will use the gradient descent algorithm, an iterative optimization algorithm capable of finding the local minimum of a function. two parameters are required: the learning rate alpha and the number of iterations n. First, the initial weights are generated randomly. Next, for n times, forward propagation is performed with the input x, which we assume for now to be a single training example. Then the gradient of the cost function is computed, and finally the weights and biases are updated. As can be seen, each iteration corresponds to a step towards the local minimum. We are now approaching the most complex part of the learning algorithm, which is the computation of the gradient of the cost function. If this video has not given you a headache so far, congrats, and I think you are ready to continue. To compute the gradient of the cost function, imagine that we are dealing with a 4 layers neural network, so something like this, that maybe it's not a network, it's just aligned with some circles. It's smart, maybe not as smart as its siblings, but it's good for our purpose. And I denote the input layer is X, then we have W1, A1, W2, A2, 3, and A3. And then I denote the first layer as layer 0, then 1, 2, and 3. So when I refer to the first layer, I mean this layer right here, and the third layer, this layer right here. The cost function J is just the square difference between A3 and the label squared. And our goal is to compute the gradient of the cost function. So the partial derivative of the cost function with respect to W3, B3, W2 and B2, W1 and B1, so with respect to the weights and biases. In order to compute the partial derivative of a composite function, we need to apply the chain rule, that same rule that we use to compute derivatives at the university. And I know that sounds a little bit informal, but with this rule, in this situation, this context, the intuition is that we compute every derivative until we reach the function with the necessary variable. So we start by computing the partial derivative of the cost function with respect to the weight in the last layer. And in order to compute this partial derivative, we need to compute the derivative of the cost function with respect to A3, in this case, then the derivative of A3 with respect to Z3, and then the derivative of Z3 with respect to W3. And just as a reminder, a generic AN is just the activation function fed with the linear combination of that layer. And then Zn is just Wn multiplied by AN minus 1 plus μn. These first two terms corresponds to the impact of the unit in the third layer to the error, and we will denote them as delta 3. Just for the last layer, delta 3 is the difference between A3 and Y, so the value of the activation function of the last layer and the label itself. Then the derivative of Z3 with respect to W3 is just AN minus 1 if we see this generalized form. And in this case, AN minus 1 is just A2. So we can say that the partial derivative of the cost function with respect to the weight in the last layer is delta 3 multiplied by A2. And what about the bias? If you want to compute the partial derivative of the cost function with respect to the bias, with respect to B3 in this case, it's the same as before. We need just to change this variable right here. So it's the same as before. Okay. And then we need to compute the derivative of Z3 with respect to B3. And if we see this generalized form, if we consider Bn the variable, the derivative is just 1. So here we have delta 3 multiplied by 1. So the partial derivative of the cost function with respect to the bias is just delta 3. And how it works if you want to compute the partial derivative of the cost function with respect to a weight that belongs to an hidden layer, for example W2. We need to apply the chain rule again, but we need to explicitly compute the delta. So we need to compute the partial derivative of the cost function with respect to W2. So we have the derivative of the cost function with respect to A3. Okay, this is the same as before. But then we need to compute the derivative of z3 with respect to a2, and then the derivative of a2 with respect to z2, and then derivative of z2 with respect to w2. Okay, now it seems complex, but it's not. Simply because these first two terms corresponds to the delta that we've already computed. This is delta 3. And these terms corresponds to delta 2. So we can say that the delta of the next layer is useful to compute the delta of the previous layer. So for computing the delta 2, we need to multiply delta 3, so the delta of the next layer, with the derivative of the linear combination of the next layer with respect to the activation function of the previous layer. And if we check this generalized form, if the variable is an minus 1, the derivative of this function is just wn, so w3. Then we need to compute the derivative of a2 with respect to z2, and it's just f prime, the derivative of the activation function fed with the linear combination of z2. Now, I would like to notice something interesting on how we compute the delta of one layer. Similarly to forward propagation, in this case we need to propagate backwards the delta of one layer in order to compute the delta of the previous layer. And for this reason, all these computations to determine the gradient of the cost function take the name of backpropagation. And finally, we can say that the partial derivative of the cost function with respect to w2 is equal to delta 2 multiplied by a1. a1 is the derivative of z2 with respect to w2. And what about the bias? The partial derivative of the cost function with respect to b2. This is the same as before. It's delta 2 multiplied by the derivative of z2 with respect to b2. And this derivative is equal to 1, so this partial derivative is equal to delta 2. So in summary, to calculate the gradient of the cost function, we use the backpropagation algorithm, where we compute the impact of every unit on the error in order to determine every partial derivative. In a generic hidden layer, we propagate backward the delta of the next layer by multiplying it with the weight and the first derivative of the activation function fed with the linear combination of the layer whose delta is to be calculated. Only for the last layer, delta corresponds to the difference between the result of the last layer and the label. The partial derivative with respect to the weights of a generic layer is the product between the delta and the result of the activation function of the previous layer. For the bias, it's just delta. Okay, now we've acquired intuition and the basic knowledge on how a neural network is trained, and we can now try to develop one for recognizing handwritten digits on a 28 by 28 image with Python. The neural network will have 4 layers, the first one with 784 units, one for every pixel, the 2 hidden ones with 10 units, and the last with 10 units as well, because this is a multi-class classification problem, so one example can be classified among 10 possible classes. In order to train the network, we will use gradient descent as we have seen, where initially the weights and biases will be randomly generated. W1 will be a 10 by 784 matrix, U1 a column vector of 10 elements, one for every unit, W2 and W3 10 by 10 matrix, and B2 and B3 2 column vector of 10 elements as well. Then, as many times as we decide, we perform the forward propagation over the entire training set in one shot. If you think about it, the training set is a 784 by M matrix. Every column corresponds to a training example, so M is the number of examples. If we perform the linear combination between the weight W1 and the training set, the result will be a 10 by M matrix. Every column is the result of the first layer for every training example. If we go on, the result of the network will be a 10 by M matrix, very easy. And this is how we perform forward propagation on the entire set. In this case, the cost function we are going to use is the mean squared error, the average error of the training set. Since we are dealing with probabilities, we should use the cross entropy loss function, but we want to keep it simple, so we stick to the mean square error. Next, in our gradient descent algorithm, we need to compute the gradient, as we have seen. The equation that I showed you earlier for backpropagation are still valid for matrix operations, just with small changes. The way they are obtained is different, but I would explain it here because it requires much time, and the goal of this video is to give the basics on the math behind a neural network. The delta of the last layer, delta 3, will be the difference between a 10 by n matrix, the result of the one-shot forward propagation, and another 10 by n matrix, the encoded labels. For the derivative with respect to W3, we know that we have to multiply delta 3 and H2. In this case, we have to perform the matrix multiplication between delta 3 and H2 transposed to match the actual dimensions. After multiplying, we obtain a 10 by 10 matrix, the partial derivative of each weight of the third layer. And if you think about it, the first row of delta 3 corresponds to the delta of the first unit of the third layer for each training example. The first column of H2, since we transposed it, corresponds to the result of the first unit of the second layer for each forward propagation of the training example. This means that once the linear combination between the first row and the first column has been performed, the element at position 11, W11, of the derivative matrix corresponds to the sum of each derivative of that single weight resulting from each training example. And we do not want the sum of all changes to our weight, but just the average. So after the matrix multiplication, we have to multiply the result by 1 over m, and that's what we want. If we want to be precise, that 1 over m comes from the chain rule applied to the mean square error. But as I said, the intuition behind it is enough for now. Okay, now we can open our blank notebook and we can start by importing the tools that we need. We need pandas, so we can read CSV file in form of data frames. Then we need NumPy, so we can deal with linear algebra. And then we need the PyPlot, because later we will plot some useful information regarding the performance of the network. In the description, there is a download link for the CSV file containing 10,000 images in form of row vectors, where the first column corresponds to the label of each training example. Now, the first thing we have to do is to read the CSV file in form of an NumPy array. And then we need to shuffle the data so we are sure that the set is evenly distributed. Now we should split the set into training, validation, and test sets. But to keep it simple, we consider the 80% of the set as the training set, and the remaining 20% as the validation set. In fact, with the validation set, we will check how the network is performing with data that it doesn't know. And this is useful to check if there is an underfitting or an overfitting problem. So the first 8,000 rows will be the training dataset. But then, since we want to deal with column vector, we need to transpose this dataset. So now the first row corresponds to the label of each training example. Then the remaining 2,000 elements, 2,000 rows, corresponds to the validation set. And as the same for the training dataset, we need to transpose these rows because we want to deal with column vectors. Okay, now we can try to print this dataset so we can see the structure. Print training set. So as you can see now, the examples are arranged in column vectors. So the first row corresponds to the label of each training example. And that's the same for the validation dataset. And now we need to divide the labels from the data we will feed to the network, considering row 0 as the labels of the example, and the remaining rows as the pixel values of each example. So train X will be the pixel value of each training example. And they will be all the rows starting from row number 1. And the labels will be just the first row. So train labels will be just the first row 0. And the same for the validation subset. So now if we print, for example, train labels, it will be a vector of 8,000 elements that corresponds to the label of each training example. Before using this data, we have to normalize them so that the pixel values fall within a range between 0 and 1. Now they goes from 0 to 255, and we can do this by dividing all pixel values by 255. At this point, we need a function that generates the weights and biases randomly. So I call it init params. And we can use some of NumPy's built-in functions. In particular, we will use their uniform distribution to generate numbers ranging from -1 to 1. So np random. So I want to generate a matrix with numbers that go from -1 to 1. And we want to generate, in this case, we want to generate W1, that is a matrix 10 by 784. We can do the same for W2. W2 is a matrix of 10 by 10. And then we have B1, B2, and B3. All of them are a 10 element column vector. B3 is a 10 element column vector as well. And then we can return these new randomly generated matrices. Then we need to define our rectified linear unit function that, just as a reminder, the rectified linear unit returns 0 for negative values and the value itself for positive values. And we can do this by using some built-in function of NumPy's with np maximum. This function works element-wise, so if we fed it with a 10-element column vector, it returns a 10-element column vector. The last thing before defining forward propagation is defining the softmax function, which is slightly different from the one that I showed before, because this version that I'm going to implement is a numerically stable version. In fact, the standard activation function, we can say, doesn't behave well with very large or very small values. As you can see, it's very similar to the one I showed before, with a small difference. In fact, from the exponent, we subtract the maximum value of the vector. At this point, I think we have everything in order to set up our forward propagation function that I name forward prop. And we feed this function with every parameter that we have randomly generated and the input, of course. And now, as you know, the forward propagation step will just complete the linear combination of each layer, Z1, Z2, and Z3, and the result of the activation function of each layer. For example, Z1 will be the matrix multiplication between W1 and the input. And we can perform the matrix multiplication with the dot function. So W1 dot input will perform the matrix multiplication between W1 and the input. And then we need to add the bias. And then A1 will be the activation function fed with the linear combination of the first layer. So A1 is equal to prelude fed with Z1. And we can do the same for Z2. Z2 will be the matrix multiplication between W2 and the result of the previous layer. So W2 dot A1. And then we add the bias of the second layer. A2 will be the same, the rectified linear unit fed with the linear combination, the result of the linear combination of the second layer. And then Z3 will be W3 dot A2 plus B3. And then the result of in this case, the activation function A3 will be the softmax activation function, softmax activation function fed with Z3. And then the forward propagation step will just return the result of all these computations. So Z1, A1, Z2, A2, Z3, and A3. And A3 will be just the chance of the input being one of the 10 classes in this case. Okay, now that we have all the tools for the network to make decisions, we have to think about implementing the algorithm that makes it learn. We know that the gradient descent algorithm uses the backpropagation algorithm to calculate the gradient of the cost function. In turn, the backpropagation algorithm needs the derivative of the rectified linear unit and the function to encode the labels. We can start by implementing the derivative of the rectified linear unit. That is a very simple function. It gives 1 for positive values and 0 for negative values. And we can do this with one single line of code. Very, very easy. Then we need a function to encode labels. We want a function such that given a label, it is transformed into a vector of 10 elements, where the position corresponding to that label is 1 and the remaining cells are 0. It's like saying that there is a 100% chance that that example belongs to a class. Okay, now we can implement the backpropagation function. It should be easy. We have already seen how it works. We have just to implement it. And as you know, in the backpropagation algorithm, we compute the delta of every layer. And then with the delta of every layer, we compute the partial derivative of every weight and biases with respect to the cost function. So in order to do this, we need to give to the backprop algorithm, to the backpropagation function, the linear combination of each layer and the result of the activation function of each layer. So Z1, A1. Then we need the input, the training set, X. And then we need also the weight of the second and the third layer, because we need to propagate backwards the delta of the next layer in order to compute the delta of the previous layer. So W2 and W3. Because we don't need W1 because we don't need to compute the delta of layer 0, layer of the input layer. And then we need the labels. So now we need to encode labels. We call it one hot. We use the function that we have just defined, get one hot, okay. Labels. And then we need the size of the training set, the number of training examples. And it is equal to x.shape 1. And in this case, we are counting the number of columns in X in this NumPy array. And now we can go into the backpropagation algorithm, and we can start by computing delta 3. It will be just A3 minus the encoded labels, the one-hot encoded labels. And now we can just implement all the operations and equations that we have achieved before. For example, the partial derivative of the cost function with respect to W3 is just the matrix multiplication between delta 3 dot and the result of the activation function of the previous layer transposed, and then all multiplied by 1 over m. And for the bias is the same. It's delta, the sum of all elements of delta 3 multiplied by 1 over m. It's a little bit hard to see, but this sum, it's also performed here, as we have seen before, but it's performed implicitly during the matrix multiplication. Now we need to backpropagate delta 3 in order to compute delta 2. That is equal to the matrix multiplication between W3 transposed and delta 3. And then all multiplied by the derivative of the rectified linear unit fed with TRLU, fed with Z2. This is not the matrix multiplication, but is the element-wise product between the matrix multiplication and the derivative of the rectified linear unit fed with Z2. So it's a little bit different. And then it's the same for the derivative of W2, that is equal to 1 over m multiplied by the matrix multiplication between delta 2 and A1 transposed. It's the same also for the bias, V2 is equal to 1 over m multiplied by the sum of delta 2, of all element of delta 2, dot sum. And then we do the same for delta 1 and the derivative with respect to W1 and V1. I've also implemented the cost function, the mean squared error in this case, because we can monitor the cost that should get smaller and smaller after each iteration, both for the training set and the validation set. That's what I hope. And now we can implement the gradient descent algorithm. It will take the features of the training set, then the labels, then the features of the validation set that I call Vx, and the labels of the validation set as well, labels. And then the two parameters that are the learning rate alpha and the number of iterations that I call its. Then we have to initialize the weights and biases, V1, W2. And then for its times, we have to compute the gradient of the cost function, and we have to update the weight and biases in order to go towards the local minimum. We take the predictions of the network, and then we use the backpropagation algorithm in order to compute the gradient of the cost function. And after the backpropagation, we need to update each weight and bias. For example, W1 is W1 minus alpha multiplied by the partial derivative of the cost function with respect to W1, and the same for W2 and W3. Keeping track of the cost on the validation in training set is a very useful way to diagnose an underfitting or an overfitting problem. Later we will plot this information, so we will see how the network will perform during its training phase. I adjusted a little bit the code because there were some problems, for example here with the order of the variables, and then after each iteration I will print the first 10 predictions and the relative labels and the cost of the validation and training set, so we can see real time how it's performing. And now to the most awaited moment of the whole video. We can train our neural network with a learning rate of 0.1, and we can start by using 3000 iterations. And now we can go. This is the graph of the cost function. The red line corresponds to the cost on the validation set, and the blue line the cost on the training set. But the good news is the fact that both of them are going down. The bad news is the fact that they are not going down so smoothly. We can see some bumps. But this is due to the fact that we didn't use any kind of regularization, so it may be understandable. Maybe in another video I can talk about regularization. Now I want to test the neural network, and for this reason I will use this library, Gradio. It is a very powerful library. We can install this library with pip install Gradio, because with some line of codes we have a ready-to-use interface where we can submit whatever we want. In this case I created an interface that takes an image as an input. I have some 28 by 28 images that I can submit, and we can see how the network will perform. I can submit this, that it seems to be an 8. Okay, and it predicts to be an 8. I can submit, I don't know, a 3. Okay, it's seen like a 3. Then a 5. Okay, I don't know, a 4. Okay, it's performing very, very well. I don't know, maybe a 6. It seems to be a 6. I don't know, something that is a little bit ambiguous. This, for example. Okay, it says that it is an 8, so there's something wrong. But it's okay. It was a little bit ambiguous. And I don't know, this last one seems to be a 4. Okay, it seems like a 1, but it's okay. It's, as I said, it's a little bit ambiguous. Okay, so the network seems to perform kinda well. We can make some improvements, but for now it seems to be enough. Okay, this video has finally come to an end. It's been a very long video. I've condensed a lot of information about neural networks, and for this reason I hope the explanations were clear enough. Thank you for watching.